the first, I have a scheduling note. All right, so today I'm going to go through chapter 2 in your book, which is a review of TCP IP. You hopefully are already familiar with this stuff. And then next week, you'll have to take a quiz before class. The quizzes are online in the online course management system, which is here. You can log in there. You have to go to this website and claim your RAM ID first, which is a very strange system, and I'm sure it's changing. But anyway, that's the current system. We are going through a multi-year painful process of switching from having about 7 names and passwords for everybody to having some kind of single sign-on, which is very cumbersome and difficult. And anyway, this happens to everybody. So you have to finish these quizzes a half hour before class. You have 2 chances to take them. And then, hopefully people will have reviewed chapter 3 before we have the lecture about it. Then there's a holiday and a guest speaker, so nothing will be due for a couple of weeks after that. But you should turn in the first couple of homeworks by next week too. They come in by email, and they're screenshots of you getting a couple of virtual machines going and showing that you can take over a Windows machine from Linux with that graphical tool Armitage. Anyway, if anybody came to add, there's room, and I'll hand out the add codes when we take a break. But let me start with the chapter 2 stuff here. And yeah, okay, yeah, good. All right. So that should, how rude. All right, I'll settle for PowerPoint. All right. Oh, there it is, just in the wrong folder. Okay. I tried to get away from PowerPoint because it runs so badly on the Mac these days. The Mac Keynote works much better. All right, so the TCP IP is a protocol stack containing dozens of protocols, but there are 4 or 5 that are used all the time. The most common ones are TCP over IP. That's something like 99% of the data transmitted over the internet uses that. That's because you use TCP if you want to make sure that your data gets there complete and unaltered. And normally, that's what you want. You don't want to see half of an image or half of an email. You want to see the whole thing. All right, so the protocols are standards written so different kinds of computers can talk together. This is very important. Usually when a new product comes out, some company just makes it and nobody else even knows about it, so you can only use that one company's product. But after you have a lot of companies that want to manufacture stuff, you have to agree on things like these 3-prong holes in the wall. The IEEE defined a standard for 120 volt AC power and exactly how big that plug is going to be and how long the wires are going to be. And everybody has to obey the standard or their stuff will not interoperate. On the internet, these things are never settled. The closest they get is a thing called an RFC, a request for comment, and this is a very detailed technical document written by a committee of IEEE people specifying exactly what TCP is, UDP, DNS, and the other protocols we use. And then people who make software and hardware that connects to the internet should obey those standards, but there is no legal requirement to, and there's no auditing of how well they apply the standards, and in fact, people do not obey the standards very well. The worst offender used to be Microsoft. Microsoft just made Internet Explorer, and their engineers just did not pay any attention at all to the standards, and they just made up whatever they want. And at that time, they were 99% of the market, and they said, those idiot eggheads can write anything we want, we are the standard. And every web designer learned that you can go study HTML and write a page, and then you'll spend most of your life making it work in Internet Explorer, which has only a passing resemblance to what HTML should be. But after the antitrust lawsuit, Microsoft got the fear of God put in them, and they stopped doing so many nasty, unethical things. And in particular, they started obeying standards, and Microsoft is now quite good at obeying the official standards and interoperating with other people, which probably not coincidentally coincides with their decline from being basically a monopoly on the desktop to really an also-ran. If you run for the last 3 years, if you look at the wireless traffic on the City College network, all Windows products put together have never even made it up to 20%. Most traffic comes from Android, and most of everything else is iPhone and iPad. Microsoft is a sinking ship as far as traffic on the internet. The only thing they own is these heavy, clunky computers that sit on desktops, and you can't even sell those hardly anymore. Nobody wants them. Everybody wants portable devices. And Microsoft's made many attempts to break into that market with very little success. They've even made very good products. Windows Phone was apparently a good product, and those little Mac Surface Pros, those things are really very good, but very few people use them. The Android and Apple products are far more popular. Anyway, so the TCP/IP stack is in 4 layers, and we'll go through them here. You may know the OSI model from taking Network Plus. Here in this chapter, they do the TCP/IP model. The difference is the OSI model was made in Europe. It has 7 layers, and it's primarily theoretical. The TCP/IP model is the way hardware is really built, and there are really only 4 different layers. If you study the OSI model, the top 3 layers are in fact all done by your browser. So the network layer is at the bottom. This is the physical network card, the cable, the network interface that moves the data. Then you have the internet layer with IP addresses. So you have MAC addresses down here at what's called the network layer in the TCP/IP model to move things on the local area network by Ethernet. Then you have IP at the internet layer, which moves things the great distance across continents and cities to find the physical location of the computer at the other end through routers and switching down here and routing up here to get there. Once you have found the right computer, you use TCP and UDP to address a process on the computer. So each computer is running several services, like an email service and a web service and a voice over IP service, and the TCP or UDP port is how you tell the computer which process you want to talk to, and the application layer is the human readable stuff above that. After all this stuff, which most people don't know or care about, the humans are at the top reading an email, viewing a video, and so on, seeing something that has been translated into something of meaning to a human. So the users live up here, and the engineers keep this stuff going, and that's where we want to be, understanding how it works. So I say protocols at the application layer are the ones that a human user will see, like HTTP in your browser and FTP to move files, email, simple network management protocol, which is like pretty much all of them, got some fantastic security flaws. Now, simple network management protocol is used to control switches, routers, firewalls, and servers. And although there is a secure version 3, almost everybody continues to run the insecure version 2, typically with a default password, because they have legacy devices on their network, which are not compatible with the new protocol. So you'll find that almost all the security problems are incredibly obvious. People continue to use things that have been known to be completely broken for decades, like FTP and Telnet. Of course, this is true of a lot of other things. I mean, why do people get sick? Because they smoke and they eat meat and get fat and stuff like that. And everybody knows you shouldn't do it, but people just do it anyway, and security is the same. All right, so HTTP moves web pages around. FTP lets you transfer files across different operating systems. SSH lets you communicate with servers with command line commands, and it is encrypted. And SSH should be a security improvement over Telnet. Telnet was originally designed before the internet. You would have a keyboard here and a twisted pair wire going to the computer over there, and Telnet was the protocol to move the data down a wire in your room. And then, when people went to the internet, they ported this to the internet, so now it sends your commands without any encryption over the internet, which is a terrible idea. All your commands, all the data coming back, all the passwords are sent with no encryption at all. Same thing's true of FTP. The SSH was intended to be the security improvement. Everything is encrypted. Unfortunately, the early versions of SSH had appalling security flaws and made it worse than ever. The early versions of SSH had a buffer overflow, so you could just take over the server through the SSH daemon, so it was worse than ever. But that tends to happen. Most progress moves by first breaking something and then fixing it. Anyway, so the transport layer, you have a high-level object, like for example an email you're trying to send to somebody, and the transport layer first segments it. You can only move a certain amount of data in a packet. This is because of a design limitation of Ethernet primarily, which can only move about 1,500 bytes of data at a time, which, by the way, is appalling. This was designed decades ago when the networks were 1,000 times slower and the data was 1,000 times smaller. So if you watch a YouTube video or a Netflix video, that thing is probably like 5 gigabytes. So it is broken up into 5 million packets, each of which is routed to you one by one, because each packet only has about 1 kilobyte of data. There are standards to make that data size 1,000 times larger, but the infrastructure is not installed for it in any large scale yet, and will continue to do it the current way, which is extremely wasteful. So 5 million separate packets have to make routing decisions to find its way from Netflix to your computer at every hop. This is so inefficient, people claim it's using at least 100 times the power and processing time that it has to use, And its last estimate I saw about 3 years ago, they said 11% of the entire power generation in the United States is used to run the internet. And it's currently running very inefficiently because the standards are very out of date for modern traffic, but this is the way it is. So TCP is the reliable protocol and the most common one, and in order to be reliable, it has quite a few measures which slow it down but make it work better. The first one is you don't bother sending data if the receiving computer is not listening. So just like when you make a phone call, you have this protocol where the phone rings, then you pick it up and say hello, then they say hello, and you don't start talking until this has happened because you're not sure anybody's listening. So TCP has a handshake that does the same thing. You start by sending a SYN packet to the other end. Say, are you listening? If they're listening, they reply with SYN-ACK, and you reply with ACK. Now you're ready. This is like hello and hello. You know, no passwords or other data is included in these packets. They are only to initiate the communication. And that is really important to us. We're going to use that throughout all the course and all hacking. You understand this handshake and you use it and abuse it, and that's how you detect processes and begin attacking them. This is the TCP header format, and this is the way it's defined in the RFCs, which are all in plain text. This is bits. So this is 32 bits across the right, so this is 4 bytes. You have port numbers, 16 bits for the source port number and 16 bits for the destination number. So there are 65,000 possible TCP ports at each end. Then you have a sequence number and an acknowledgement number, and that's what's actually set up by the SYN-ACK. You agree on some sequence number and acknowledgement number so that you can number all the bytes of data. If you send this way, if you send packets of data and some of them get lost or drive out of order, each one of them is labeled with a number so you can reassemble the file at the other end back into its proper state. Down here are some things that don't matter that much to us right now. Here's the pointers: urgent, ACK, push, reset, SYN, and FIN. And the SYN and the ACK are single bits set here. So the first packet has this bit set and none of the others. The SYN-ACK has both of these set, and the ACK has the ACK bit set, and those are the 3 packets in the handshake. After that's done, you will then transfer data. You've logged in to do something, presumably, like send an email. So you send some data. The window size determines how much data you can send before it must be acknowledged. Typically, it's something like 8,000 bytes. So you send several packets, moving 1,500 bytes at a time until you transferred 8,000 bytes. Then the other end sends an acknowledgement back with the ACK bit, which includes a cryptographic checksum to make sure that it all got there correctly. And if you don't get the ACK, your computer will resend it. This provides flow control. The destination, well, a very common situation is the server is fast and powerful, like Google's server. Your receiver is slow and weak, like a laptop. So Google could send data far faster than you could process it. So the receiver determines the speed with flow control. Google sends me only 8,000 bytes, and it doesn't send any more until my computer replies and says, okay, I'm ready for some more. That's how it works. All right, the end result is that TCP moves data much more slowly than the maximum transmission path of the wire because it sends just a little bit, and that takes time to get there, and then the acknowledgement takes time to get back, and it doesn't send any more until that happened. So in order to make sure that the data got there intact, you pay a lot in speed. All right, so those are the critical components for us, are the flags, those single bit things like SYN and ACK. The initial sequence number is useful for an old-fashioned session hijacking attack that is not that common anymore, but was really the cat's meow in the late 90s. And the port numbers are very important. So we talked about these. All right. The initial sequence number is just counting the position of this data compared to other data that might be in the same TCP stream. And if you're using insecure protocols like FTP, and you can predict the initial sequence number, which was possible in the late 90s, then you could take over a session, and this is what Kevin Mitnick did with the session hijacking attack. He was the #1 most wanted hacker, counted by the FBI for a couple of years as he fled from city to city. They couldn't catch him because he was such a good hacker, and he could hack into the phone network and intercept and tap the FBI's phone calls, so he knew what they were planning, and he would run away before they could catch him, and he humiliated them. So they finally caught him, locked him up for 9 months in solitary, and now he's finished his prison term, finished his parole time, and is now free again, and now he's a security expert. He's a really nice guy. I've always wanted him to come talk here, but he's such a celebrity, you can't get him without paying money. Anyway, one of the things he did was he would take over servers this way, which is pretty easy. Back in the 90s, the initial sequence number would just start at one number, and then the next person that connected would just get the next number and the next number, just in order. So all he would do is connect to a server and load the web page, then call the administrator on the phone and say, ha, I just hacked your web page. The administrator will now connect over FTP. He knows that's going to happen. He can predict the sequence number of those packets. So he waits for the administrator to log in and then intercepts, taking over his session by guessing the right number, take over the session after he's logged in. And here's another fun fact about networking. A lot of devices make duplicate packets. It is fairly common that a router or a switch, there's some packets waiting, and something happens that causes them to be delayed, and they're resent later. So you might very well get 2 copies of the same packet at a device. And all the devices are programmed to ignore this silently. If you're waiting for a packet on a certain port number with a certain address and a sequence number, and you get it, and then later another one with the same sequence number and same port number and address comes in, is just silently discarded. So that's how this attack works. If I can sneak in my command before the real command, it'll believe that I'm the administrator and not just kick that person off. So it's a cute attack, but it doesn't work if you use encrypted protocols, because then I cannot forge a packet that will really fool the server, because there's a secret key that I don't have. Anyway, the TCP port is just a number in the packet. It's named this way after the physical ports on your devices, like a USB port and an Ethernet port, because for practical purposes, it means it's as if you had your own cable to use. I connect to the server that there's this thing called a socket, and let me show them to you live. If I bring up my command line here, make it bigger. All right, so if I want to see the network connections on this machine, this is a Mac, so it's running Unix. I do netstat -an pipe-more, which is exactly the same command on Windows, by the way. And here are some sockets. I am connected from a local address. I happen to know this is my local address because I'm on the City College wireless network, and everything here starts at 147, 144. So this is my local address. This is my local port number, which is a really big number, less than 64,000 and change. Then I have a foreign address somewhere, which is some server I'm connected to, and this is the port 443. Now this, by the way, is not the correct notation. There should be a colon here instead of a dot, but the designer of the netstat utility on this system broke the rules a little bit. But I just invite, this is my local address, this is my local port number, this is the remote address of the server, and the remote port number, and this combination of 4 numbers is what's called a socket. That means now I have a local process on my machine with that port number and a remote process on the server, and the 2 of us can exchange data as if we had our own wire just for that use. That's why they call it a socket and a port. It's as if I send a cable to the internet service provider and had to plug it in there and plug it in here. Now the 2 of us can talk, and the data will not get mixed up with anybody else's data, at least as long as there's no evil hackers out there sending forged packets. And you have a state. This established state means that the handshake has completed. Sin, synac, ac. And you'll play with this in the lab. You'll be making these handshakes. All right. And every computer these days typically has a bunch of network ports open all the time, because even if you're not viewing websites, you're going to email, your computer is synchronizing the Dropbox and checking for updates and doing various things. There was once a time in the 80s and 90s when people wanted to control their computer, and you did not connect it to networks much, and you only put on software that you bought that came in boxes on floppy disks. But now we're like fish swimming in dirty water. It's constantly flowing in, you don't even know about it, so you have to be running antivirus, like fish swimming in polluted water and taking antibiotics. That's the way we are. You're constantly taking in highly untrustworthy junk like Windows updates, which are fantastically impure and unsafe, and you have to compensate by putting other things on to prevent some of the harm that comes out of it. It's sort of crazy. And if you use Windows 10, it is spectacularly crazy. Last semester we used Windows 10, and every couple of weeks VMware would quit working because Microsoft pushes down the updates, and the updates just keep breaking stuff. You think you're going out of your mind. You can even open Windows in the administration panel, and the button you need to click is gone. And then next week it's back again, and you say, wait a minute, this is madness. But that's the way it is these days. It's kind of nuts. So you can block ports. Now, if you just plug in the cable and run it normally, all the traffic that's addressed to your machine that has a strong enough electrical signal on the wire and such will come in. And that's the way computing was originally done, and that's the way it's still done with things like iPads and iPhones that do not have any security problems you have to worry about for all practical purposes. But Windows machines and Android machines are under attack and they are vulnerable. So you now have another bit of madness. You have a network card to let network traffic in, and then you put a firewall on it to block some of that traffic. Now this is like the difference between this college, you just have a door, you open the door, everybody can go through. But if it was City Hall or the Hall of Justice, there'd be a guard and a scanner, so we have a door, and then we have another system that limits who can get through the door, and that's the way most computers are. So you have a network card, and then you have a second layer of guards examining all the packets coming in and out. And the simplest, the first generation firewalls just did this by port. And you should still do that. So if you are running a server that is a web server and an email server, it's serving up web pages on ports 80 and 443 typically for unencrypted and encrypted web pages. And it's receiving email on port 25. So you want to block all the other ports. So that even if somebody manages to hack in and start a process, or somebody by accident starts a process on another port like TFTP, it won't cause any harm because it can't receive any traffic on that port. So this is what you do, is block ports you're not using. This is called reducing your attack surface, where you just lower the number of open doors with which to enter your server. And from a simple intuitive point of view, you would imagine that reducing the attack surface will make you safer. No one knows if that is true. There are pretty strong arguments that it is not true, and this is why I should mention, as I try to do in all my early classes, there's a strong argument that everything I'm teaching you is all worthless, because there are no security metrics in this business. Nobody really knows how secure a network is, and after you make changes, like hire better professionals and install some fancy gadgets, nobody really knows how much better it's gotten. They would like to say, your current security is a 3, but after you buy our $1 million firewall, it will be a 4, and that will mean you'll have $10 million less worth of hacking this year. That would be great, but we have nothing like that. There are no scale, there's no index, there's no measure that means anything. It's all just intuitive. So that's kind of a problem with this business. We are still going by intuition. Anyway, on we go. So you can't block all the ports. There's 2 categories of ports. The original RFCs made 3, but Microsoft fouled it up so much that now we're pretty much back to 2. The first 1,023 ports are called well-known ports. I think it's actually 1020. I think it is actually port 0 to 1023, but I don't think people use port 0 hardly ever. Anyway, those are not well-known just because they're famous. They're reserved for the purpose of running really important services on the internet, like HTTP and FTP and Telnet. So operating systems require you to have administrative privileges to listen on those ports, because those are important ports. All the other ports can be used for any arbitrary purpose, like a game or a chat client or something. So here's the most famous ones of those that you should know. You want to pass any certification exam in this business, people expect you to have the top 10 or 20 ports memorized. 20 and 21 are used by FTP for file transfer protocol. Everybody should have had file transfer protocol blocked at their firewall for the last 30 years. It is a sin and a shame. The only use of FTP that makes any sense is anonymous FTP, like Microsoft. Microsoft, as is very commonly the case, is doing the right thing. Microsoft is a pretty secure group now. They used to be terrible, and they got humiliated enough to shape up. And so Microsoft runs an FTP server, at least they used to. Let's see if they still do. Maybe not. I think City College does, so let's start that one while this one is loading. Right. I may not be able to find one to show you. But anyway, an FTP site, an anonymous FTP site, is an extremely boring thing. It's just a list of folders like you might see on a floppy disk, and you can just download files. And if you want to do that, that's not an insecure thing to do, but it's not a very pleasant thing for the user. It would be better to have an HTTP page so you can have an explanation, say click here for this and click here for that. It's just a list of files. A lot of companies have them just as a convenient way to distribute security tools for their in-field reps or something, and that's harmless. But FTP has the ability to protect your data with a password, and that is anti-security. There are security measures that place you more at risk, and this is one of them. If you have passwords going over FTP, they're transmitted in plain text so everybody can steal them. So think about what you have done. You have handed passwords to the criminals so they can use them. You have irritated your staff by making them remember and type in passwords which they may forget. You have not stopped the bad guys from getting in. You've made it more difficult for the good guys to get in. This is the opposite of security. That's why everyone should have blocked it 30 years ago, but they continue to use it. And Telnet, just out of stupidity. And you'll find that most security problems just mean some idiot just left the door hanging open. So that's FTP. You connect with the name and the password, which is then sent in plain text and harvested by malware on the server and the devices in between. And anybody can follow you with those passwords and mess with your site. So port 25 is SMTP, Simple Mail Transfer Protocol. Port 53 is DNS, that translates alphabetic names like ccsf.edu into numerical IP addresses. Your DNS traffic therefore reveals everything you do. It doesn't expose your passwords, but it exposes your browsing history, every site you go to. And that is why it is considered pretty awful that most privacy solutions, like VPN services, do not encrypt the DNS traffic, so they really don't protect your privacy very well. Port 69 is Trivial File Transfer Protocol. This is a protocol that makes it possible to push files from one computer to another without any password at all. There is no provision for a password in the least. It's used on local area networks to upload firmware into smartphones and into routers and switches. And it can be used to send poison firmware up on private networks. It was used to send worms. Back in the days of 2000, there was worms that would come in over port 69, so when you plugged into your dial-up modem and connected to the internet, you would get infected even when you were not browsing the web or opening email or anything. It would just come right up because Windows 2000 ran a TFTP server that was on all the time, and you didn't even know that. This was because Microsoft's design decision at that time was intentional. They said, we want our products to be easy to use and security does not matter. That was the official position of Microsoft until 2002. So your 2000 machine had everything turned on. It was an HTTP server, a Telnet server, an FTP server, and people didn't even know this. So you put up a website and people would just connect over Telnet and hack it, and they say, how did this happen? We didn't even turn on Telnet. Well, everything's on by default to make it easier to use. And after the hacking situation got bad enough, Microsoft reversed course with the 2002 security computing memo from Bill Gates, and they gradually switched their entire company to the opposite posture, where if you buy a modern version of a Windows product like 2012 server, it doesn't do anything. You have to turn on everything, which makes it much harder to use and much safer. And Microsoft has moved that way. So port 80 is used to browse the web over good old HTTP, which I must say, HTTP is going down in popularity very fast now. Many people have said we should be encrypting more web pages, and now I find more than half of the sites I go to are secure using HTTPS. 110 and 119 are not that common anymore. 135, 137, 139, and 445 are used by Microsoft File Transfer to share files and printers over the local network. They are extremely risky. There's an endless chain of worms attacking these ports because it uses remote procedure call. Unix has the same thing, but a remote procedure call asks the server to run some code for you, and you can offer many services on the same port. And what has happened is, I'll be going through this quite a bit in the malware analysis class. Microsoft is brilliant. This is the Microsoft remote procedure call thing is kind of brilliant and kind of insane. And the way it works is this. You originally would write a program to run on one machine, and it would have different components, and the components would talk to each other by sending signals within the computer. And Microsoft made a system called DCOM, which makes it very easy to take code designed for that environment and expose it to the internet. So now people on the internet can send signals to the same code and use it. So this means tons of code that was intended to run inside one machine is now running over the internet. So if you didn't really consider security very important because nobody could get at it except the user, the same code is now connected directly to the internet and people can hack in. So this turned out to have many flaws, but it also makes it very easy to make money selling software, which was Microsoft's goal. You can design a component in a limited space and with a small modification make a commercial product and sell it to people, which means if you want to write a program, you can just buy code from people, plug in the modules like Lego, and build your code. So it's very efficient to make money, and that was Microsoft's official policy until 2002. Our goal here is to make a computing platform that makes it very easy for developers to make and sell products, and for all the products to work together so people can efficiently make code that people can use, and security is a waste of time. That was their official position until 2002. And so anyway, these ports should be blocked at your firewall because there's an endless chain of vulnerabilities in the many services served by them. 143 is another older email protocol, not that common these days. And I've shown you some of these. Showed you some of these connections before. I don't think we need to go through it. But let's look at the handshake. The handshake is important. So Wireshark is your best friend. Wireshark is how you really learn networking. You can see the packets coming in and out of your network. So I can sniff my Ethernet adapter, and it'll just show me all the traffic. Most of the traffic is sort of baffling and not too important ARP, but what you can do is filter the traffic. So I'm going to find by IP address. It's apparently this, 147, 144. Let's try this. I'm going to try telnetting something. I wonder if City College still allows me to telnet. They used to. They don't. Well, they finally blocked it. That's just as well. All right. I think I'll just connect to one of my servers on port 80. So I'm going to limit this to, say, HTTP. Okay, so there's a series of code words and there's an expression builder. So now I'm going to see only HTTP traffic, and there isn't any. So now if I go to a browser and I open a plain HTTP page, like one of mine is ad.samsclass.info. Okay, there's one of my pages, and it's not encrypted. It's a plain old HTTP page. There's no padlock or HTTPS up here. So we should see it in Wireshark, and we do. So here's the game. This is the HTTP exchanges that loaded that page. Now I'd like to see the handshake, and by using this filter, I blocked it, so I'm going to remove that filter. I'm noticing I'm at packet 636 here. Shortly before packet 636, I can see the steps that led to that. So here is the whole story. It came out very nicely here. Okay, when I try to go to a page, the first thing I do is send a DNS request. The user typed into the browser ad.samsclass.info. You can't contact a server with that kind of information. The only thing it accepts is numbers, IP addresses. So this query asked a DNS server, where is samsclass.info? It got an answer. That server is here, 159.203. Now that you know the number, you can talk to the server at 159.203 and so on. So these packets go out, and let me adjust it so you can see them. All right. This is my local address going to the server, 159.203, then the server replying, then me going back, and so I sent it a SYN from port 56,550 to port 80. It replied with the SYN ACK, then I got the ACK. That's the handshake. So first comes DNS to find the address. Once I have the address, I do the handshake. Now I can exchange data. And so once I've got that, then I get an ACK. I send a GET. Show me the page, and I get an ACK saying I received your request. Then I get 1,500 bytes of data, and it finishes with a 200 OK saying here's the page, and then I send an ACK saying I got it. So you can follow this stuff in Wireshark with follow TCP stream, and it will show you the layer 7 exchange, which is quite useful. This is what a GET looks like. I'm getting a web page from a server. It is always, you tell the version of HTTP here, which is almost always 1.1 these days. The slash means show me the root of the page. I just want samsclass.info, the main page, not a sub page. It might be in a folder. So then I tell it, this is the name of the server I want. You have to tell it this because you can serve many pages from the same IP address. And this is why you can get cheap or even free web hosting. They can host 100 web pages on one server. So they all are delivered in response to GETs going to the same IP address, but the host name is different. Then you have data down here that is not essential, but commonly sent, things like what the name of my browser is and which version I'm using, because you could have a server that serves a different page to different browsers. Most desktop browsers all get the same page, but most professionals now send out a different page for phones, because obviously the phone is smaller and you have a special version of your page. So it does pay attention to that to decide which version of page to serve. And then things like whether you're going to take data that's zipped or not, and cookies, which identify who you are. If I was logged into some service like Facebook, the cookies would be a code so it can tell who I am and whose Facebook wall to show me. This is just a Cloudflare cookie. All right, then I get a HTTP 200 OK, which tells me that it found the page and it's serving it to me. There's a server from the header, and down here's the content. And in this case, I was willing to accept it in zipped format, so this is zipped content. And so that's the first bit of content, and then comes some more, and it loads the page. First it loads the HTML, and the HTML may contain things like image tags and movies, and then it has to make further requests to load all the other pieces and slowly build the page. That's how it works. And Wireshark is your best friend for networking. You certainly want to get good at using Wireshark. There's even a Wireshark certification. I've been tempted to teach it. I haven't yet, but it's quite good. Book Wireshark 101 is very good. And if you're good at running Wireshark, it's a very good skill to have. Yeah?
So when you go to your bank account, for example, and you have that, can you be able to see the password and stuff?
Usually not, because it's usually encrypted. And in fact, I'm glad you mentioned that. Let me just demonstrate that one too. Let's go to a secure page. Because we're about to take a break, and it's a logical thing to finish the demonstration here. So let's go to, say, google.com. And that is secure. See, it says secure right there, HTTPS. So let's see how that looks. If I stop it and I remove the filter, now I'm going to look for Google. This is something I learned, which is good, clean fun. Frame, learned it from that book, contains Google. If you have any plain text in a frame, you can do this, and then it will show you the frames that contain Google. And here's the one, Google APIs. I'm going to do it with a less popular site because my machine is contacting Google all the time because I use Chrome. Let's see who else is secure. How about the NSA? NSA.gov. I hope their page is encrypted. It is. Well, that's good. So the NSA has an encrypted web page, and I should be able to see how that loaded. So let's try frame contains NSA. Oh, how rude. How did I get there without doing a DNS rex? Oh, perhaps I'm not sniffing? Continue without saving. Right. How about CIA? CIA.gov. Okay. Now, let's see what happens now. If I stop, I should have packets that got me to the CIA. There we are. I was losing my mind there for a minute. All right, so to get to the CIA, the first thing I have to do is find its address, and that is done without encryption. Like I say, this is why most people are typically spraying their entire internet history everywhere around them, like in your coffee house and the other people in your home network, because every time you type in any alphabetic domain name, it has to be resolved, and that's done with an unencrypted packet. So here I'm asking, where is the CIA? So I get an answer, and it tells me the CIA is here, and eventually it's going to come up with a number. So this 190 looks like where the action started. So let's clear the filter and see what happened around 190. Okay. I sent a query. Here I am connecting to the CIA with CNIT. Now I'm connected to their server. Now the secure handshake is a more complicated affair. First you have, let me shrink down these parts I don't care about. All right, so first I send CNIT. Now I'm able to send data to the CIA and get data from the CIA, but it's not encrypted yet. So the first thing I send is a thing called a client hello. Now the client hello tells I want to start TLS, transaction layer security, which is encrypted traffic. But I don't yet have any keys or anything. So I send a client hello message, and if you look at that client hello message, let me fit it on my screen here. Okay, it's going to tell you what protocol I'm speaking, and it's going to have a long list of curves and stuff down here, like elliptic curves. I can take 4 types of elliptic curve and all these other things. What this is doing is saying, I would like to speak to you with encrypted traffic. In order for that to work, we have to agree on an encryption protocol. So since I'm the client, I'm going to tell you, what have you got? If I am Windows 95 running IE3, I only have a few really weak encryption options. But since I'm Chrome on a modern Macintosh, I've got a lot of them, and they're pretty good. And we could speak with elliptic curve cryptography, we could use elliptic curve Diffie-Hellman or a variety of others. I offer it. Here's a dozen encryption routines I could use. Do you speak any of those? And then the server can decide which one it wants to offer you. So that was my client hello, and then there's an acknowledgement saying it got it. Then comes the server hello. And the server hello will make a choice out of all that junk saying, okay, let's pick one of them and use this one. We're going to use, I'm not quite sure how to find it in here, but someplace in here, yeah, we apparently agreed we're going to use elliptic curve and one of these. It offers me one. Yeah?
So, if you have an older system and you're communicating and then you don't have the language,
yeah.
what complaint did you get?
That's a very good question. This is a deadly attack called a downgrade attack. If you can intercept this traffic, which is not encrypted, for example, by being in the middle of the coffee house, you can change it. I'm on my Chrome on a MacBook in a coffee house. Someone could be in the middle and tell the server that I'm IE3 on Windows 95, and I can't handle any key longer than 40 bits. And the server, if it's a well-configured modern server, it will refuse to communicate with me. It'll just say error message, I'm not doing that. I'm not going to talk to you, go buy a better computer. But most people don't do that. Most people, their server has been up for years, nobody is paying attention, and their server still has those really old protocols in the list. So when I say, I can only speak 40-bit encryption, it says, okay, fine, no problem. And now it will cheerfully communicate with me over an old broken protocol. Now that's a downgrade attack, and this will come back again and again. There are many times where you can trick someone into using the old version of something, and almost always the old version is much less secure. But if, in my case, of course, that's not happening, I'm offering it good options, it picks a good option, so after the client hello comes a server hello, then we have a key exchange, and now we can encrypt data, and from now on, after that's all over, now we send data with, there'll be encrypted session data down here, there it is, application data. And now the application data is just unreadable. If you look at that, it's just gibberish like this, because it's all scrambled, and the key is exchanged in a secure, very secure way, and nobody's getting in there, unless they have got malware on my machine that is stealing the data before it gets encrypted. Decrypting this stuff once it's properly encrypted on the wire is almost impossible. And that's the point of it. So anyway, it's just about 10 minutes to 10. Let's take a 10-minute break, and when you come back, grab one of these eye clickers and leave your name behind in the slot it came out of. You can write your name on a scrap of paper or put an unimportant thing there like a student ID. Don't put credit cards or money in here, because I don't have any way to stop students from taking each other's things, but come back at 10 and we'll carry on here.
Okay, what do I write?
Just put your name on there, just so we know which one you took.
And a number?
Yeah, well, just in the
stick it
slot your
in
number, yeah, good. And I'm gonna stop the recording,
21.
yeah. And
Somebody,
there's
there's a
123.
name already in there.
Yeah, just take it out, yeah, just cross it out and throw it away.